Okay, so we're going to finish up problem number 4. Here we go. Oops. This one is the car tire, and it makes a certain amount of revolutions, and the question is, what is the angular acceleration? Okay, and we mapped out our information, the number of revolutions, which I'm going to convert to radians. This we have to eventually get into an omega. Now notice that these are linear. Okay, we have to go from linear to angular, so we're going to be using this relationship to do that, where the angular is the velocity divided by the radius, and then we're going to this is the diameter, so just be careful with that. So actually what I'm going to do is take that and find the radius by dividing the diameter by 2. 0.4 meters, which is where this is going to come in. So let's convert these to meters per second, and then we can put it into radians. So 95 kilometers per hour times in 1 hour, there's 3,600 seconds, and in 1 kilometer, there's 1,000 meters. And I'm just going to do this as one big step. So that will get us our velocity meters per second. And if we divide this by r, so 1 over r, the radius, I'll get the angular. And you'll notice that that basically takes out all my units except for the seconds, and we're left with radians per second. So 95 times 1,000 divided by 3,600, and then divide by the radius. So we get 10.56 radians per second. Kilometers cancel out kilometers. Hours, hours, meters, and meters. So we have a number over seconds. So radians is, like I said, is kind of an interesting unit because it's almost like it's unitless. This is just a number divided by seconds like that. So I'm going to go ahead and do this same calculation here, like this. It's exactly the same because we're converting the same numbers. So like I said, again, I'm going from velocity to an angular. But this, of course, is not in meters per second, and then we have to take this and divide it by r. So that's why there's this extra step here, because we're dividing by r. So 45 times 1,000 divided by 3,600 divided by 0.4. I think I made a mistake somewhere. Let me just double check these numbers. Okay, that would make more sense. Looks like, okay, let's do that. There we go, 65.97. That looks a lot better. Okay, I was wondering about that. That did not look right. Perfect. Okay, now we're in the right ballpark here. Alright, now that conversions are done correctly, we have basically, it goes from here to here. So this is omega I that we found, and this is omega F. Alright, the other thing we have to convert is takes our 65 revolutions and make it into radians. In 1 revolution, there are 2 pi radians. So let's do that. 65 times 2 times pi gives me a 408.2 radians. Alright, now that we have all of this, I can use omega final squared equals omega initial squared plus 2 alpha theta. So with that said, our final is 31.25 radians per second, whole thing squared, 65.97 radians per second, whole thing squared, plus 2, And then A is what we're solving for, and then this is the 408.2 radians, like that. So solving for alpha, 31.25 squared minus 6597 squared divided by 2 divided by 400.2. Great. We get negative 4.13 radians per second squared. And it's negative because it is slowing down. So this is the rate at which rotation is slowing. So that's essentially what this means. And then part B says if the car continues to decelerate at this rate, how much more time is required to stop? So we could figure out how much time it takes for this, and then how much time it takes to stop, and then we can compare the two. So with that said, I'm going to use omega final equals omega initial plus alpha t. So originally, we get this, our final is 31.25 radians per second equals the initial, which is the 65.97 plus negative. Now you can just write this as negative, but I'm showing you that I am following this rule right here, times t. So 31.25 minus 65.97 divided by 4.13. So this takes 8.41 seconds like that to slow down. But then it's asking, what about if we go to rest? So this would be 0. Our starting velocity. And it says, assuming we had the same acceleration. Should be squared. Like that. T is equal to 15.97 seconds. So how much longer? Basically, we take the difference between the two times to get the time difference. So 15.97 minus 8.41, 7.56 seconds difference to come to stop. So that is these 4 problems right here for rotational kinematics. Since I have some more time, I'm going to solve a few more problems. Okay, so this is the other part of the video which I'm going to solve. It's another torque problem. So why don't we take a look at this. So in this case, we have a wheel with several forces applied at some radius away, so we're going to get a torque on our system. So calculate the net torque and assume we have a frictional torque, okay? So in order to solve this, first we have to figure out the net torque on the system, because that's going to tell us the direction of the net torque. And once we know the direction, we can then figure out what our sign is for our frictional torque, which is given right here. So that's kind of where we're going. So let's start with the first one right here. So I'm going to solve for net torque. Now net torque is essentially this counterclockwise minus the clockwise torques. Now I wrote it as counterclockwise because convention is that counterclockwise is positive, which makes the clockwise torques negative, okay? So my first step is to figure out which ones are going clockwise and counterclockwise. So if you take a look at this one right here, this is going to make it go clockwise. So I actually like to label that, like right next to it, which makes this, of course, negative. This one is going counterclockwise, so I could write that as counterclockwise or positive. And this one is going clockwise, so this will be negative like that. So that gives me the signs. Now let's figure out our net torque. So I'll start with the positive one, which is that one. Now for torque, if you recall, torque is going to be force times the radius times sine of the angle. But if you look very carefully, you'll notice that all the forces are actually perpendicular. So here's the radius, here's the force. This is 90 degrees right here. So from here to here, notice that this is also 90 degrees. And despite this angle, which is actually meant to throw you off, the radius from here to here and the force are actually also perpendicular. So I'm actually going to drop this because this is 1. And remember, the reason why is sine of 90 is equal to 1. So for all these, I'm just going to multiply the force times the radius. So starting off with that one, I'm going to do the force times the radius. Now the radius is mentioned as 24 centimeters from here to here, but notice I converted immediately into meters. Then we're going to subtract our other forces, which are counterclockwise. So if you notice, this is 0.24 away like that, and this one is 12 with a 35 Newton force, like that. So this is going to get me the net torque on my system. So I'm going to do this calculation out. Sorry, I'm doing this out. So I get a net torque of this, which is, as we can see, it being negative, this tells us the net torque, I could write this the same way, is 1.8 meters, and the negative, remember, means clockwise. So if our net torque is clockwise because of the negative sign, then our torque from friction has to be opposing that, so it actually is going to be a positive value when we add that in. So, finishing off, torque net will be our net, which is, you can leave it as negative like that, plus our friction. So that is the 0.4 meters, like that, which gives us a negative 1.4 meters Newton as a final net torque. And just to recap, what I had to do is figure out first what the net direction is so that I can apply the right sign to our friction. So we kind of did this in two parts here. You can see that. And I'll just write this out. What we did is to find the net torque, we took the, net torque minus the friction, like that. And even though I have it as minus, recall that this is going against my motion, which is actually positive. So this is written like that. And our net torque is negative, so this is going clockwise if we needed a direction. But that's how you can solve that. So in the next video, I'll solve another torque problem. Or actually, I think I might be able to have time to solve this one. No, I'll solve it in the next video. I'll see you in the next video then.